Okay, welcome back. Let's have a look now at another topic, which is learning rules. So first, some definitions. So learning, again, is a process by which three parameters are weights and bias of neural networks are adapted through stimulation from environment. Learning also can be defined as a sequence of events simulated by an environment. The system undergoes changes of its three parameters. The system responds in a new way to the environment based on a sequence of events. A learning algorithm, definition of a learning algorithm is prescribed steps of a process to make a system learn. It is also the way or the ways to adjust the synaptic weight of a neuron. There is no unique learning algorithms, so a kit of tools. And in this lecture, we will cover 5 learning rules or 5 learning paradigms, and including probabilistic and statistical aspect of learning. But before we do that, let's review gradients and derivatives. And talk about the gradient descent minimization, which is an important optimization approach used in lots of supervised deep learning approaches, and also even in meta-learning. So gradients and derivatives. So differential calculus is the branch of mathematics which deals with computing gradients. So if you consider function y equal f of x, this function y, this y is a function of x, and the gradient or the rate of change of f of x at a particular value of x. So if you take a particular value of x, as we change x, as we go from x to x plus delta x, from x to x plus delta x, the gradient or rate of change of fx at a particular value as we change x can be approximated by delta y divided by delta x. So it's this rise of a run, or we can write it exactly or formally as the partial derivative of x with respect to x, which is the limit when delta x, this delta x goes to 0, of the function f of x at x plus delta x in here, minus the function of f of x divided by this delta x. And this is f of x plus delta x minus f of x is simply delta y, is this change here. So it's the, and this is known as the partial derivative of x with respect to x. So some examples of computing derivatives, and this is from very basic. So for example, if you have a function ax plus b, which is the equation of a line, the partial derivative of x with respect to x is the limit, and you replace f of x plus delta x here. So this is your f of x plus delta x, minus f of x divided by delta x, you find a. So the derivative of this ax plus b is simply a. The derivative of ax squared is 2ax. The derivative of a sum is the sum of the derivatives. Other useful derivatives is the derivative of ax of n is nax n minus 1. The derivative of the exponential is a times the exponential itself. The derivative of the log is 1 over x, and the derivative of the sine is the cosine. Just a reminder. So what is the gradient descent minimization? So suppose we have a function f of x and we want to find the value of x that minimizes this function f of x. What we need to do depends on the derivative of f of x, so the gradient. And there are 3 cases to consider. So if the gradient f of delta f, the partial derivative of f with respect to x is positive, then f is increases as x increases, okay? So what should we do? Because we're looking for the minimum, so we should decrease x. If the gradient is negative, which means that f of x decreases as x increase, so we should increase x. If the gradient equal to 0, then f of x is at the maximum or minimum or optimum, so we should not change x. If we're looking for the minimum here, yeah, we can look for, check if it's a minimum by computing the second derivative. In summary, we can decrease f of x by changing x by this amount. So if we're at, so this is the delta x. So we change x new. So it's delta x is x new minus x old minus delta or eta, this gradient value. So this is how we should move to along the x to reach the minimum, to minimize f of x. This eta here is a small positive constant, which specifies how much we change x by, and the derivative of, so this is a learning rate in our learning algorithm, and the derivative delta f, this gradient here, tells us which direction to go in. Should we go this way to look for the minimum, or this way? If we repeatedly use this equation, f of x will keep descending towards its minimum. And that's why this procedure is known as a gradient descent minimization, assuming that eta is sufficiently small. Because if eta is large, as we're going to see, we may end up or we may miss our global minimum. So type of learning, again, another review is we have the supervised learning or learning with a teacher. So the teacher has knowledge of the environment to learn. Input and desired output pairs. So you have a desired input, desired output are given as a training set. The parameters are adjusted based on the error signal, step by step. So you have an error signal, a distance between the desired and the actual output, and the desired output of the system is provided by the teacher, okay? And this is, again, our supervised paradigm. So you have a system, an adaptive network where you feed X, you get an output. The difference between the actual output and the desired output is fed back to train this network. So you know, you have this, you know the ground truth, you have the desired output, as opposed to the unsupervised learning paradigm, where you don't have a desired output. So that's why learning with teacher estimates the negative error gradient direction and reduces the error accordingly. So it modifies the synaptic weights, the weights to reduce the stochastic minimization of the error. So your goal is to minimize this error here in a multi-dimensional weight space. So here you assume that, for example, in the case of a multi-layer perceptron where you have a large number of weights, so it is a multi-dimensional weight space. So you move towards a minimum point of error surface. It may not be a global minima, so you may get stuck sometimes. So you start from your point here, you move along the gradient descent, and then you may get stuck in a local minima while you're looking for a global minima. So it may not be a global minima. Use a gradient of error surface, direction of steepest descent to look for your global minima. And it's good for pattern recognition and function approximation. So this, yeah, this is a learning. This is how you get your learning. The self-organizing learning. So the desired response is unknown. You don't have an explicit error information. You don't have that row, which can be used to improve your network behavior. It's suitable weight self-adaptation mechanism or mechanisms have to be embedded in the training network. So the system learns by itself. You don't have any external teacher or critic to tell you whether you're doing it right or wrong. The task-independent measure of quality is required to learn, and the network parameters are optimized with respect to a measure. So we're going to see that one of the paradigm competitive learning rule is a case of unsupervised learning. Again, this is with teacher, without teacher. You have another paradigm, so you have the supervised, unsupervised, and you have also the reinforcement learning. So in this case, you don't have any teacher to provide direct or desired response at each step. So for example, in the case of the broom balancing problem, where you have a broom or and then you want to excite it and then teach the system to keep it. This is the inverse broom balancing problem. So you have a broom which is inversed and you want to maintain it stable. So what you do, every time you excite it, if it falls, you give it a punishment, give the system a punishment. And then if it stays, when you're excited, if it stays the same, you give it a reward. So so you have an environment, and then you have a critic, which teaches the system based on its response, whether it gives it a reward or a punishment. And that's how the system learns. You tell the system, you're doing good, you're doing bad, you're winning, you're losing, this kind of thing. So before we go on, let's look at some terminology. Again, the training set is the ensemble of inputs which are used to train the system. So for a supervised network, it is the ensemble of input, desired output, response pairs used to train the system. So you have the input and the desired output, or the ground truth. The validation set is the ensemble of samples that will be used to validate the parameters used in the training. You should not confuse it with the test set, which assesses the performance of the classifier according to certain performance criteria. So first, you train the system, you validate to make sure that the parameters are okay, and then you go to the test set, which is, you test the system. So you use the training set, which is the ensemble of input, desired, response data used to verify the performance of a trained system. So this data is not used for training. So this training set, the data, the samples that you have in your test set is not used for training. So the system has not seen the test set before. A training epoch, so you have your training set. A training epoch is one cycle through the set of training pattern. We've seen it for the case of the end function. You want to train the system and allows it to, you would like it to generalize, to be able to generalize, to perform well, even with the samples that it didn't see before. Okay, you don't want it to memorize completely, so that when it sees a new sample, it won't do well. You want it to generalize. So just like you teach us a kid, 1 + 1, you get 2, 2 + 1 is 3, 3 + 1 is 4, and so on. And then you say, oh, okay, what is 4 + 5? And it didn't, 4 + 1 or 5 + 1. And they didn't see this example before, but it is able to generalize. So it is the ability of a neural network to produce reasonable responses to input patterns that are similar, but not identical to the training pattern. So again, you are assuming that the input patterns are similar to the ones that have been used in the training set. For simplicity, there are cases where, you want to transfer knowledge, transfer learning, and so on completely from, so that's a more advanced topic. Asynchronous versus synchronous updates. So asynchronous is the process in which the weights or activations are updated one at a time, rather than all being updated simultaneously. So you do it, you adjust this weight, and then you adjust the second weight, the third weight, and so on, one by one. As opposed to the synchronous updates of the weights. In this case, all the weights and the parameters of the system are adjusted at the same time. You have inhibitory connection. We're going to see that in the case of the Hebbian rule, as opposed to the excitatory connection. So inhibitory connection is a connection link between two neurons such that a signal sent over this link will reduce the activation of the neuron that receives the signal. So in this case, you're reducing the activation. And this may result from the connection having a negative weight or from the signal received being used to reduce the activation of a neuron by scaling the net input that the neuron receives from other neurons. So these can be the causes of the reduction of in the activation of the neuron. What is an activation? Is a node's level of activity, the result of applying the activation function to the net input to the node. Typically, this is also the value the node transmits. So after the activation function, when you've seen the perceptron, so the activation, so you have the activation is the summation, and then you have the activation function. Okay, a review also of vectors, because we would need that. So again, you have a reference, you have a vector, a 2D vector in this case, which has a magnitude, and this angle here are defined by this. You can define it in the Cartesian axis. This is the polar representation of this vector. You can also represent it by its component. So this is your vector. This is the projection on the x1 axis. This is the projection on the x2 axis. So the module of this vector is the square root of v1 plus the square root of v2. Sorry, the square root of v1 square plus v2 square. So this this value here, v1, the projection on x1, and then the square of the projection on x2. The inner product, so if you have two vectors here, v and w, the inner product of v and w is v1, w1. So v1 being the projection on x1, and v2 is the projection on x2. And so v1, w1 plus v2, w2, or the sum of I from 1 to 2, or n if you're in an n-dimensional space, vi, wi. It can also be defined, the dot product, as the norm of v, norm of w, cosine the angle between them. So in this case, it's 45 degrees. So this is phi. Okay, the projection of v on w, so if you want to project v on w, which is called vw, is the norm of v times the cosine between the two vectors. Okay, and then if you use this here, so if you're looking for v cosine phi, so you can write vw as the dot product divided by the norm of w. If you're projecting on a on the x-axis on the I, so the norm, you're assuming that you have an orthonormal basis. So the norm of I would be equal to 1. An important property of the inner product to measure the similarity between two vectors. So if your dot product is greater than 0, that means that your angle between the two vectors v and w is less than 90. So they are close to each other, okay? As opposed to if the dot product is 0, they're perpendicular to each other. If the dot product is negative, that means that they are far from each other, okay? And this is the cosine, this cosine Measure can be used, can be measured as a similarity between two vectors. We stop here. Thank you.